Good, great. So Wei Cao from Yale, and she will talk about optical kernel machine with programmable nonlinearity. Again, I get up at 25 minutes, and then 30 minutes you finish the talk, and then there's still 5 minutes. Thank you.
Okay, thank you. First, let me thank the organizer, Clara, and Florian for this invitation. Really my pleasure coming back to Max Planck Institute. I've been here many times. Every time I really get excited. So first I have to say that I know little about optical computing, so I'm very excited coming here to learn more about this. And so I really appreciate this overview from Dimitri. Really tell us what is the future or what is the possible opportunities for optical computing. So today I'm going to talk about something quite narrow. That is, we're trying to using this optical kernel machine with programmable nonlinearity. So I think you probably know more than what I do, but I'll just still give a brief introduction to the students here. So about this kernel machine learning. So a kernel machine can learn nonlinear complex patterns by mapping the data to high-dimensional, high-dimensional spaces. So they are usually quite effective with limited data. So that's why this kernel machine learning allows nonlinear modeling with tractable computation. But the problem is that typically if you're using this electronic or digital kernel machine, the size of the this kernel matrices scales quadratically with the number of samples. So therefore the scaling is really poor if you have a large data set. So because of this issue, in recent years, people have been trying to explore optical implementation of this kernel machine. Why to do this kernel-based computation using light? Because we all know it is very fast, has high bandwidth, low latency, and also it allows this massive parallel processing with reduced energy consumption. So there are many potential applications people have been talking about. For example, high-speed signal classification, imaging or spectrum recognition, and also chaotic system prediction. So for those optical kernel machine, we know that nonlinearity is very important. I think Dimitri has been talking about how to achieve optical nonlinear response. So indeed, that for a kernel machine, we want very strong nonlinear responses so that it can operate at low power with high efficiency. We also want it to be stable and robust, free of any nonlinearity-induced instability. So more importantly, we hope that this nonlinearity of this kernel machine, they can be tuned continuously at constant power. So this will allow us to optimize the kernel nonlinearity for diverse tasks. So also like Dimitri mentioned briefly about the structured nonlinearity. So this is different from mature nonlinearity. Typically you need a high peak power. But here actually structured nonlinearity it really relies on the nonlinear optical response of structure to the structure change. In other words, the nonlinear output signal is depending nonlinearly to the structure change in a linear system. So there has been different ways to realize structural nonlinearity and in different frequency domains. For example, in microwave, Philippe Dohorn and also Roman Florid, they have been working on this in like microwave cavities. And also here at Max Planck Institute, Clara and Florian has been working on this proposal of nanophotonic, chips. And also, I think Dimitri mentioned his group and also my group, we have been trying to using this kind of free space implementation based on multiple scattering of light. And also Professor Oskan in UCLA mentioned, have been using this phase encoding to SLM to do that. So there are many ways. I also missed other references here. But I wish to here in this talk, I mention our implementation. We're using multiple scattering of light in disordered medium. Here, we can consider a material with a lot of scatters. So when the light coming in, fly in, it will go through multiple scattering, and then the transmitter light field, we consider this a phi out. Because the system is linear, so if you consider the output field, it depends linearly on the input field, and this T here, we call the transmission matrix. That complete map the relation between input field and the transmitted field. So this is a linear system. However, because of multiple scattering, when we can try to decompose this T by a Born series. So here we show the V is a scattering potential. G represents the free space propagation between two scattering events. So you can see here we can decompose this into single scattering, double scattering, triple scattering. Because there are many different scattering events here, you can see that actually the output field will depend non-linearly on the scattering potential. So in other words, that if you have some change of your scattering structure, the output light will change non-linearly. So we call this is a structure nonlinearity. So in our case, we actually simply implement this structure nonlinearity in a 3D scattering cavity. So here shows here, we have a laser, a continuous wave laser output at 20 milliwatt. We inject into like a three-dimensional scattering cavity with a rough inner wall here. And then one of the openings, we actually cover that with this kind of a digital switchable mirrors, which we call the DMD. It contains about 4 million pixels or micro mirrors there. And then so the light, when they come in, they will go through multiple scattering by this DMD, and also the rough wall of this cavity. After multiple scattering, some light will escape, and then that can be collected by a mirror and directed to a camera. So in this case, when we write some configuration to this DMD, which provide a reconfigurable scattering potential, and then you can see that this output will be a speckle pattern, which is this random grainy pattern that's coming from interference of those scatter light. And this mapping from the DMD input to the output speckle pattern, that is nonlinear because of recurrent light scattering to this DMD micromirror array. So in this case, we actually continue the nonlinear order continuously at the same input power by just changing the size of the modulation area. If we have a larger modulation area, then it has more chance to interact with light. So in this case, you have more or additional light scattering that will lead to a higher order nonlinearity. So we actually quantify how nonlinear this response is by doing a linear fitting between the input to the DMD and the output speckle pattern. So this basically shows the linear fitting coefficient of determination, R squared, which goes down as we increase the DMD modulation area. To have a more quantitative understanding of this structure nonlinearity in this disordered cavity, we actually perform some numerical simulation. We consider a two-dimensional scattering cavity with the rough wall here. And then on one side of this cavity, we have this 12 mirrors that can be flipped into two different positions, just like in the DMD. That corresponding to we call the -1 and 1. Then we have the light coming in from an input port scattered by this mirror and the boundary. Then we calculate this output field. So in this case, to really control how much times light will bounce off this micro mirror array, we actually change the the reflectivity of the rough boundary by introducing, absorption to this boundary. Then what we do is we want to say how we quantify this nonlinearity. We're using something, actually, people call this a Boolean function analysis. This is for binary input. And then this Y, this output, can be field or intensity. And then this N means the location of this output. K, it is the representing this mirror configuration. So these variables, x1 to xm, that is the binary input for this N mirrors. So this Boolean function analysis actually can give you, us multiple terms. And the first term, there's no interaction with the mirror. The first term is a first scattering, one scattering with the mirror. This one is a second, term is a double scattering, triple scattering, all the way until m. So you may ask why there's no m plus 1. Why can't you scatter more? Because it's a binary input. If you do m plus 1, you must scatter from one mirror twice. Then if we know for binary, no matter whether it's 1 or minus 1, you squared it, you're going back to 1, right? It doesn't matter. So then what we do is that for each order, we actually we sum of all this expansion coefficient for the same order. Then we average over the output position and also the micromirror configuration. So here shows this Boolean function analysis for this contribution of each order, which with this expansion order to this total output. Either output is field or it is intensity. So we can see here is that as we increase the reflectivity of the wall, which means we increase the dwell time of light inside the cavity, they can bounce in more from the mirror. Then you see that this Boolean function analysis shows the higher order contribution or nonlinear contribution increases. Of course, for if we have only 51% reflectivity, for the field, it peaked at the first, which is a linear scattering. But for intensity, it peaked at 2. That's because you have E squared. So that's why the intensity usually have a higher nonlinearity or nonlinear order than the field because of this quadratic, because of this square. So this basically tells us that we have a stronger wall, reflectivity that will increase the dwell time of light in the cavity. Then light will bounce in more from those switchable mirrors that can give us, higher nonlinear order. So to quantify this nonlinear order, we actually calculated the mean order by consider the contribution for each order, and then have this kind of weighted sum that is normalized. So what we show here is that as we increase the wall reflectivity, the mean order increases. Okay, so that's basically tell us we have higher order structure nonlinearity at the same power. So the next what we are saying that what we do is we do some ray tracing, and from this ray tracing, what we find out is that the mean number of bounces of light of this micromirror array is actually scales linearly with the mean order. In other words, the mean order of nonlinearity for this structure nonlinearity, they increases linearly as we have more and more bounce of this mirror. Okay, so after this one, we say, okay, now if we wanted this one to using this for maybe for computing or recognize what is the, for this kernel machine learning, we want to see how the output sensitivity, how sensitive the output of this, multiple scattering cavity to the input change. So how can we quantify that? We sending, say 2 input to this micromirror array. We calculate what is their correlation. Then for the output field, we can first minus the mean value, and then we calculate this output field correlation. And we see how that depends on the structure nonlinearity. So here shows the input correlation versus the output field correlation, the real part. So if we have a linear input-output mapping, it will give us a straight line. However, if we show this, if we see this two color, that is, we have this output from this 2D scattering cavity with different wall reflectivity, we see that actually they are deviate from this linear scaling. So if we start with, all the input are the same, they're correlated with 1, of course your output has to be correlated. That's a deterministic system. But as we moving away, we change the output away, and then you can see that if we have a stronger nonlinearity, it actually will decay faster, or stay more, faster than linear. So that means that your output will decorrelate faster with a stronger structural nonlinearity. And that will be useful for this system to have a diverse response, because they kind of quickly forget what is the initial input there. At 0, which means input uncorrelated, output is also uncorrelated. That's why they are both 0. But as we go to the negative input correlation, especially when we go to -1, meaning the input is anti-correlated, you just minus the sign. The output actually, if you have a structural nonlinearity, is no longer equal to -1. That's because if you have a high order nonlinearity, if it is an even order, then you go from -1 to 1, the output is the same. So that's why we have stronger nonlinearity. You have more this even order nonlinear terms that can make them more deviate from -1. So this is for numerical data for the output field sensitivity to the input structure change. Now, if we can also do experiments, we can measure the intensity to see how the intensity correlation changes with the DMD modulation area that is actually changing the structure nonlinearity. So you can see here that actually as we increase the DMD modulation area, we actually have, again, this blue line shows more deviation from a straight line here. So that basically tells us the stronger structure nonlinearity can give us higher output sensitivity to the input structure change. And that is actually will be useful because that will increase the expressivity of a kernel. Higher expressivity means that this kernel is has a high very flexible. They can really capture this very intricate nonlinear pattern in the data. But however, on the other hand, this large variance, low bias, it is good, but it also means it's more subject to noise. So if you have a high noise in your data, we can tune the structure nonlinearity to reduce the expressivity that can make the kernel more rigid and robust to noise. So another thing what we tried is we try to check what is the information capacity of this multiple scattering kernel. So what we do is that we write many random patterns to the DMD, and then try to measure the output intensity pattern, and then we actually unwrap them to a column. Then we generate many patterns, form a matrix. This is called the response matrix. Then we perform singular value decomposition to find what is the singular values. And then we also, for a given SNR in our experiments, we can calculate this called information capacity. So here we show how this information capacity increases as we increase the DMD modulation area for our experimental signal to mean noise ratio of 21. So this increase, basically what it tells us that when you have a stronger structural nonlinearity, you can have a larger information capacity. So why that is important? Because that basically tells you that, what is the degree of freedom of your kernel. In other words, what is the, dimensionality of your output feature space. For, a larger information capacity tells you have, more channels above the noise level, which means you can have more degrees of freedom, or you can have a larger dimension for your output feature space. So with that one, with studies, we go through this kernel regression. Basically, the idea is that to map the input to a high dimensional space where this target can be extracted from the linear model. So here we basically write binary input to a DMD, and then we measure the output spiral pattern. So from that, this gives us this kind of feature space. And then it can be high dimensional because we have 1 million spickles output. And then we can using a linear regression to really estimate the target function. So in this case, by tuning the structure nonlinearity, we can really tune this kernel nonlinear capacity in order to really match the nonlinearity of the target function we want to estimate or approximate by this kernel. So here we're using one example, which is a parity function of varying order. This is for binary variables of dimension m. So xi, it is this input to each digital mirror, which has two positions that corresponding to -1 or 1. And then this parity function we consider order L. That's defined here. L will be less than m or equal to m. So this parity function of high order, they are highly variable and nonlinear. So usually they are very difficult to learn. So from the state of art that we can find is that people can get to 4-bit or they call it 4-bit XO or the parity function of fourth order, and the accuracy is about 80%. So we see for our multiple scattering cavity, what is the highest order parity function we can learn, and also what is accuracy we can achieve. So in this case, so let's start from the simplest one. We start with just the first order parity function. That is the simplest. Then we actually we can show this test error by we have 90% for training, 10% for testing. This thing is a testing error as a function of the modulation area from the DMD. We can see the error goes up. That's because when you go to a larger modulation area, you have a stronger structural nonlinearity. It's more deviated from a linear input and output mapping. So this actually can be confirmed by the first order Boolean function, coefficient. This is basically was tell you what is the linear contribution to the output. It actually goes down as we increase the modulation area. So that is expected. And in this particular case, we actually, the input data dimension is m equal to 9, and the number of output modes we use is 55. So next we go to second order parity function. So now you see that this arrow now changing non-monotonically with the DMB modulation area. At first, as we increase the modulation area, the arrow goes down, then later it goes up. So this is actually consistent with the second order contribution of, from the Boolean function analysis. It first goes up and then slightly going down. So this basically tells us that, if you have, too small modulation area, the mapping is, the structural nonlinearity is too weak. So we have underfitting. If we go to a too large modulation area, the structural nonlinearity is too high, then we have overfitting. So there is an optimum, modulation area give us the appropriate, nonlinear order that can best approximate this second order parity function. Then we go to the third order parity function. We can see it actually, this arrow goes down monotonically with increasing modulation area because it's become more nonlinear. And then this is also the third order contribution goes up as we have a higher modulation area. That's because structural nonlinearity is higher. It's better approximate a nonlinear function. And then we go to fourth order parity function. So in this case, actually, as we now we show the test accuracy is a percentage of the test sample will give us correct prediction. So as for the m equal to 9, for 9 input dimension, we see this test error accuracy was increased, eventually reach 100% as we increase the output mode number, meaning the number of speckles we're using for this kind of mapping. If we increase the input dimension, this increase is slower. We need a larger number of output modes in order to reach 100%, but we still can reach about 100%. This is better than 80%, what people have shown. Then we say, let's try to see, can we do fifth order, parity function? If we have input dimension m equal to 9, we cannot, the accuracy always stay about 50% until we got about 5,000 speckle grains at output. But if we go to m equal to 14, the input dimension, then we can see accuracy still increases go up to 92%. For the output speckle number is about 4,300. So they can keep going up if we further increase the number of output modes. So with that, let me try to summarize what I just showed you. Basically, I show you that we can have this optical kernel machine with a programmable nonlinearity. This is implemented by linear multiple scattering cavity with the spatial modulation of the main scattering structure. It allows us to tune the nonlinear order at constant low power. So this, so that we can optimize the kernel expressivity and the degrees of freedom for specific tasks. In particularly, I show you today that this kernel can represent a parity function from first order to fifth order. So the future works, sorry for the typo. First, we can try to further enhance the structure nonlinearity by reducing the loss of our cavity. We can also, here we do monochromatic light, single frequency. We can go to broadband light or pulse that can add in the spectral or temporal degree of freedoms, not just the spatial degrees of freedom. That allow us to do this kind of multiplexing to further increase the expressive power of our kernel. And also maybe we can try the real-time in situ optimization of this structure nonlinearity for specific task. So finally, if I have maybe 1 or 2 minutes, I just want to give a comparison between structural nonlinearity to material nonlinearity, because there has been a lot of work on material nonlinearity. So typically, material nonlinearity is either second order or third order. Why don't go to higher order? Because the peak power limited. But for structural nonlinearity, as I show you, we can go higher than third order with the same power, and also continuous wave. And also, if you consider material nonlinearity, when you decrease your power, if you want to go to lower power, your signal decrease nonlinearly. For second order nonlinearity, the decrease of the signal is quadratic with the power. Third order, it is third times. But for the structural nonlinearity, the output power is independent of nonlinear order, and it scales linearly with the input power. So that means even I send in single photons into my cavity, they still experience multiple scattering. They can still experience this high order structural nonlinearity. And finally, this optical signal usually for structure, if you're using material nonlinearity, second order or third order, you can change the wavelengths. If you do change the wavelengths, then if you want to cascade it, your wavelengths will keep changing, and that is an issue. But here we have no change of signal wavelengths, so it's maybe easier for this cascading of this nonlinear processor. So finally, I would like to thank all the people who have done the work. This is my current and former students and postdocs. We have a good collaboration with Sylvain, Jigan, Feixia, Bruno, Wooly, and Niels. And finally, thank you for your attention.
Thank you very much for the great talk. And again, we have good time for discussions. So, first question there.
Thanks a lot for the great talk, especially thanks a lot for this great explanation of structural nonlinearity. I have a quick question. So if I understand correctly, here when you increase this M parameter, that means the pattern you have on your SLM is larger, right? Mm-hmm. So if I understand correctly...
No. Okay. Please go ahead. Yeah. Now I see the confusion. Okay. No. So the question is the DMD modulation area changes with input dimension, right?
Exactly.
That's the question. No, because you see what we do is we have this base pattern, which is you can determine either 3x3, 4x4, or 5x5. And then because our SM has millions of pixels, so you just repeat it to occupy certain area of DMD. That is our modulation area.
Yes, exactly.
So it's not related to the base pattern, which is the number of input dimension. So you see the pattern N that is repeated. So the dimension is not changing. Even I change the modulation area.
Yes, so my question is, I am in the impression that when you have a large M, the number of times you have the same pattern is lower. Is this correct?
Yes, correct.
Then what happens if what you take as a parameter is not the area of the SLM that is occupied, but rather the number of times the pattern is repeated? Do you get the same picture, or does this change a bit the things?
Oh, I see. So the question is that if I if I fix this n, right?
Yes.
And then I just changing this, this number of patterns there, right? So you see that in this case, we only changing the structure nonlinearity. We don't change the input dimension. And we do see the structure nonlinearity is getting higher, and our performance is getting better for, if you try to do a nonlinear, like a function. Did I answer your question?
Somewhat, but we can, I'll come back.
Sure.
Nice talk. I could ask you about 10 questions, but let me pick the parameters. Now, in your case, when you train the system, it's all the digital size post detection, right?
Yeah, so when we train this one digitally for this kernel machine, it is a linear regression
classifier on the intensity of the speckle pattern.
Yeah. So we measure the speckle patterns and we do a linear regression. And then we got into this, target function we wish.
But why don't you put some parameters in the optical system as well?
Try to modulate these things here, right? Or maybe adding something here. Yes, you can do it. I see what you have done. You can also try to pre-train this kind of things here. That's possible, but we have not done that. Yeah, I think that's definitely doable. I think that's probably can further increase the performance here too. Yes.
So I'm curious, I forgot my question.
Okay, I'll come back to you later.
And if no one, yeah.
Thanks for the nice talk. You mentioned of the information capacity, there was a numbers on the y-axis, like 25, 26.
Yeah.
Can we generalize these numbers, or is it setup related? How can we interpret these numbers of the information capacity?
Okay, so how can we what?
Interpret these numbers.
Okay,
what does it mean to have information capacity of 25 or 26?
Okay, so that means this is actually okay. So what is the physical meaning of information capacity 25, 26? That gives you effective number of you can say either for channels or for degree of freedom in your output. Say this is like a principal component analysis. Your output has all this kind of changes, right? At the end of the day, all these changes probably can be just expressed by 25 orthogonal vectors or patterns. So that gives you what is the dimension of your output feature space, or tells you what is the degree of freedom you have in this system. Because I can have, say, I have a lot of speckles, but do you really have, some of eventually it can be redundant.
Thank you.
Thank you. Any more questions? Dimitri?
So just to put a kind of counterpoint to all this, I mean, in the literature, there's a lot of you approximate a function by a polynomial, Taylor series or something else. There's algorithms to do this. And for a high-dimensional function, very quickly become intractable.
Exactly. Exactly.
Yeah. So the question is, since this is a polynomial expansion in the end,
Yeah.
I worry that this will also be intractable in this domain as well.
Yeah, so the question is whether this is intractable if you go to even higher order, right? Yeah, I think that, I don't know. So I think the question is, we'll give a try to see how much can we do. But if you think about it, even for your, SLM things here, if you're bouncing the number of times, if you go to 10 times, you probably can do, 10. But as you said, we do need a more and more output dimension in order to really reach out, for example, 10th order parity function. Right now, our output, speckle pattern is, so, okay, I don't know. the question is, we have to try. How much can we go? Okay. Yes.
I just wanted to comment on your question as well. And so when you showed the expansion of the Green's function, basically you have a Taylor series, but essentially you also have the higher orders, right? And so even though you calculated a mean order, you will also have the higher orders. And
Yeah.
I think if you look at the Green's function, it's actually closer to maybe a Padé approximation or something like that. Yeah, then yeah, exactly. Then a Taylor expansion. But we can discuss about this as well.
Padé is nice because you have two lower order expansions and you have to take the division.
Okay. Yeah. Thank you for the comment. Yes.
Okay, great. So let's thank Wei Shao again. Next talk will be by Martin van Hetke. Great, while he's setting up.